So, hello, my name is Asad Mirza, and I'm going to be doing a MATLAB workshop part 2, and this is going to cover advanced plotting, image processing, and signal processing. And I'm a PhD candidate in the biomedical department. There's for EMBS. Now, don't worry if you can't quickly follow along, type in the code or anything. After this event, I'm going to be sending this PowerPoint along with the scripts I've written to Alejandro, and he's going to upload it along with the video to YouTube. And then you can just directly get the files from there and then follow along at your leisure then. For now, just sort of soak up the information like osmosis or something. And I'll be pausing periodically, asking if you have any questions. So I am having my eye on the chat as well. So let's begin. Advanced plotting overview. So oftentimes when you want to just plot data, it's not just going to be a simple X versus Y. So for this little section of the seminar, I'm going to be going over various more advanced plotting techniques. Specifically, I'm going to go over multiple ways to plot on one graph, how to use subplots, 3D plots, bar graphs, histograms, scatter histograms, word clouds, surf contour, and geographic plots. And here's an example of a type of surf elevation plot you can have with a heat map that shows the elevation of a mountain in this case. So, how do you plot multiple plots on one graph? The simplest way is to use what's called hold on. So you have your data and you plot your first graph, and let's in this case sine, and then you can type in hold on, the command hold on, and then your next graph, and then this will plot the second part of your graph. So in this part, let's just switch over to MATLAB. So you have your sine, your cosine, and if you do your first plot, you get this. And now if you do hold on and then your second plot, you get the second plot and they plot on top of each other. The next thing I want to show is how to do subplots. So the way subplots work is they essentially create a arbitrary grid of size n by m, and they are numbered from starting from top left to top right and then going down to the next row. So this is position 1, this is position 2, this is position 3, this is position 4. And in this case, it's 2 rows, 2 columns. One graph is taking up position 1, one is taking up position 2, and the 3 and 4th position are being taken together by this single graph down here. And the notation is always how many rows is your subplot, how many columns is your subplot, and what position do you want this plot to be in. And then if you want to plot across multiple, you would specify how many rows, how many columns, and then which spots are going to be taken up by the following graph. So you do subplot, your first plot, and it shows up there. Then you do sits, you have to keep the number of rows and columns the same. And now you do a second plot. And now 3 and 4 are going to be taken up by this last part. And that's as easy as it is. Now you can extend this to any number of dimensions. So subplots are really useful if you need to plot many different things all in a single figure. So let's say you're dealing in 4 rows, 2 columns. And I made this little for loop here where for each index in this subplot, I'm just plotting some random numbers. And in this case, when I run this code, you can see here we have 4 rows, 2 columns. Or if you wanted to, you could have 4 rows, 10 columns. And you can see here they're all spaced nice and evenly. And this way you can see how it's sort of infinitely usable. You can have as many or as small as you want them. I know, for example, Dr. Dtrending likes to use these a lot for looking at channel recordings of many, many different signal inputs all at once. So that's one way you can do it. Next thing I want to go over is 3D plots. So naturally, you're not restricted to just 2D plotting. You can do 3D plots. So if you have X data that's going from 0 to 180 degrees, you can have one variable Y, one variable for cosine, or 1Y, 2Y, and then you can have a third one, and then you plot all 3 of them at once against each other. And in this case, one dimension has a sinusoidal shape to it. The second dimension is going to have a cosine shape to it. And the third one is just going to be linearly increasing. And what ends up happening is that you just have basically a cylinder that as you go increasing in the z, which is represented by this x, it just increases linearly, which is why it's just x. And run this code. And you can see here. If you take a look at just one dimension, so this is the xy, it looks like this. The xz looks like this. And the yz looks like this. You can also have bar graphs. So this is better for conveying relational data that might not be as numerically strict. So in this case, I arbitrarily said, okay, X labels are years, Y labels are US exports as a share of GDP. And if we run this, you can plot a nice little bar graph and edit this as you see fit. Next thing would be histograms. Histograms are good if you want to show the distribution of a single variable. So in this case, I'm doing the rand n function. So this is going to give me as many randomly normally distributed numbers as given by the second input. And because I'm doing the normal distributed, this can be Gaussian. And you're going to see this nice Gaussian shape show up. And naturally, if you reduce the number, you get sort of a normal shape, not too much. I believe there's this law of large numbers or something in statistics. As you make this number larger and larger, you reach a normal distribution, which is what you reach here once you provide enough samples. Now, here's the really cool thing that you can do with histograms. You can make what's called a scatter histogram. So if you want to show two plotting variables against each other, and you want to see how they're interacting with each other, you can do something like this. So in this case, we're going to load this built-in data set to MATLAB called patience. And let's go ahead and do this. So load patience. And just to better show what exactly this is, we're just going to load in patience. And this data set has age, diastolic pressures, their gender, height, last name, their location, if they're a smoker or not, as logical 1 and 0s, their systolic pressures, and what their weights are. And you can plot these against each other and see what's going to happen. So first, let's make a table using table. And if we do this, we create a table of the values that has their last name, their diastolic pressure, systolic, and whether or not they're a smoker or not. And we're interested in seeing, is there a relationship between their pressures and if they're a smoker or not? So you can do a scatter histogram where you give it the input of the table, you provided the diastolic and systolic for X and Y, and the group variables that's going to color it by is the third one. So if they're a smoker or not. And if we do this, you can see here, systolic, diastolic, and in blue is if they are a smoker, and this orangey reddish is if they aren't a smoker. And what you should see is, for if you are a smoker, generally it seems that you'll have higher systolic pressures and higher diastolic pressures. So perhaps this would be interesting to examine further. You could maybe even start fitting a sort of a regression curve, separating somebody into smoker, non-smoker groups, depending on if their systolic, diastolic pressure matches some sort of threshold. But this is one way you can examine your graph. Another thing you can do is you can change the display style of the curves on top and bottom to smooth. And when you do it like that, and I'm just going to do a little subplot here. Now, rather than just having this coarse shape here, you can see a better distribution of if you're not a smoker, you're generally over here. If you are a smoker, you generally fall within this diastolic pressure. And likewise for systolic, if you are a smoker, you're in this higher region here. And if you're not, then you're here. But it seems like there's a better delineation between a smoker and non-smoker for diastolic pressures than systolic. So maybe this will help you better delineate your data. All right. And one more thing, I believe this is the last one, is word cloud. So if you're dealing with a bunch of words that you want to start comparing against, and for example, let's say you're dealing with a bunch of technical reports of some device issue, and you want to see, okay, what's the most common thing that people are saying in all these reports, and you don't want to read through all of them, you can start parsing these words, and you have a very long list of just words, and you want to see how often does a certain word repeat. For example, water damage, electricity, or something like that. And this way you can use what's called a word cloud. And it just shows you a distribution of the words depending on how much they're mentioned in a list. In this case, we're going to look at Shakespeare's sonnet table, and you just call word cloud with the table, and that's pretty much it. So if I do clear again, and we take a look at what this sonnet table is, it's just a table that shows the word in question and how many times was it repeated across Shakespeare's sonnets. And you see here some words were repeated more, some repeated less. And what you can do is you can just pass this into the word cloud function and then see which one is the most shown. And it looks like which, the, their, beauty, heart, standard Shakespearean words. But you can easily swap this for technical reports, damage reports, and see what shows up the most. Next one is geographic plots. So in this case, if you had data from a Excel sheet, so let's say it was this sheet right here, and then this is a data sheet of tsunamis. So it gives you latitude, longitude, the year they occurred, the month, date, hour, minute they happened, if they were a tsunami or not, if it's questionable, the cause of the tsunami, so was it an earthquake, a volcano, something meteorological, the magnitude of the earthquake, where it happened. If you're dealing with this type of geographic data, what you can do is you can use the read table command. If you do the read table command, so read in that Excel sheet, and you should get this nice table here that has that exact same information. And anything that MATLAB does not know how to import in, it will give it a none. And now that you have this data, you can go ahead and say the causes are categorical variables. So the causes here, right now these are all strings. You can tell by the little quotes, but we're going to turn them into categorical variables of just earthquake, volcanoes, unknowns, and such. And if we do this, now we can use the geobubble command, pass it the entire table, and we're going to plot the latitude, the longitude. We're going to take a look at max height, and we're going to color everything by this cause categorical variable we just specified. And if you do that, give it a second, and there we go. Oh, let me run this again. There we go. So now you can see here you have a nice little map that's colored and dotted by your data. You can see here the size of the bubbles corresponds to the max height of the tsunamis, and they're colored as well by the cause of them. So the majority seem to be earthquakes, but you have some, for example, along the San Andreas fault line here and this sort of ring of fire, where it's actually being caused a lot by earthquakes, landslides, volcanoes seem to be in some regions here as well. You also have meteorological down here as well. Oh, apparently by the Great Lakes as well. So this is how you can take a look at geographic information. And the last thing I want to show is surf and contours. So let me advance my plots. So for surf and contour, it's best if you have 4D data. So for example, 3 spatial dimensions and 1 more dimension. So it could be time, temperature, something to color code everything by. And then what you can end up doing is you can do surf and contour. And in this case, we're trying to plot this complicated x squared plus y squared square rooted function with this sine of r over r for z. And we're going to see what it looks like. So first we create a mesh grid. That's going to go from -8 to 8 with a spacing of 0.05. We're going to calculate what our radius is using x squared plus y squared and our square root, Pythagorean theorem. we're going to calculate our z's by taking the sine of r divided by the radius. And now we're just going to pass each of these x, y, and then color it by z. And if you notice, it's completely black right now because we haven't put a shading to it. So if I try to move this to the side here, and I run this shading term, now you get color. You can pass it a number of color maps. So a color map I like using is jet. You can change the resolution by typing in a number here. It's best if you do it in units of 2, so like 2, 4, 6, 16, 2, 4, 8, 16, 32, powers of 2 essentially. And in this case, I use 1024. And you can add a little color bar. Make it axis squared. So now you can rotate without getting distorted. And add your X, Y, Z labels. And in this particular case, the coloring is based off of Z, but you can have the coloring based off of some other choice variable, in which case you would just have that be another input into your surf. And then you could, for example, look at the relationship between this and another variable like temperature or something. And I think that is it for plotting. So that does it for advanced plotting techniques. Any questions before I move on to image processing?
Everything's fine, thank you.
I didn't know you could rotate the actual contour once you finished it. That was pretty cool. Reminds me of SolidWorks.
Yeah, a lot of things you can do in SolidWorks you actually also do in MATLAB, at least as far as like viewing 3D files and stuff. But like with everything, just so much to learn, not enough time. All right, so if there are no other questions, moving on to image processing. Don't need this anymore. All right, so now on image processing. In the first webinar I did, I showed you guys how to import images. Now we can do some basic processing on them. So what am I going to go over? Some general tools that you'll need to work with images in MATLAB, and how you can do image enhancement. So contrast adjustment, histogram equalization, sharpen, and then denoising an image. Specifically 2 types: how to denoise salt and pepper distorted images, and how to denoise an image using a convolutional neural network. Here's an example of some image processing results I found online. So in this case, it's a recording of a human hand that is showing temperature, and you can plot the change in temperature across the line here. So you can see as once you're not touching the person's fingers, you see the very low temperature, and then it spikes, drops a little, spikes, drops a little again, and then spikes again. You can use this to create little line plots as you're going across the image of the temperature of the person. So that's one example. So as a refresher, you can load an image using IMRead, and then you can show it using IMShow. And these images that you're reading, they have to be inside your current working folder. And what we're going to do is we're going to convert the image to grayscale, because often when you're doing image analysis, as nice as color images are, they don't really help you a lot for image analysis, because often you're interested in the features of an image. And a feature of an image are things like edges, shapes, all that is not color dependent. So going back to MATLAB, do a clear as soon as we close all. And in this case, I'm doing IMRead on this Office 1 JPEG. MATLAB can read JPEG, PNGs, TIFFs, raw image files, the works. You can read it up on documentation, but chances are if it's an image file that you're using, MATLAB can read it. So you can go ahead and read this file. And if you notice, it's 600 by 903 by 3. And this 3 indicates that it's an RGB image. So red, green, and blue, there's a matrix for each one. And what we're going to do is we're going to convert this using the RGB to gray function. And we're going to turn this into just a single matrix with a unit 8 format. And then we're just going to do IMShow. And you see a nice little dark image. Now, one thing I want to show you guys is this tool called IMTool. which is a general all-purpose image editing tool that MATLAB has. And the way it works is you just give it the image as an input, and that's it. So if you run this, you should see this little tool come up. And this image and this tool lets you, for example, measure distances in pixels on your image. You can also crop using this. You can also adjust contrast. So you have this little contrast bar here, and you can start moving this to better see parts of your image. And you can also start to just remove outliers once your image is adjusted. Then you can start examining pixels. So if you click this Examine Pixels button here, Inspect Pixel Values, it opens up this separate window here, where depending on where this marker is, it takes you to the exact values for the pixels around the image. And you can drag this around and examine your pixels. So you can see here mostly dark values here, wider values here. And images are restricted from 0 to 255. So 0 corresponds to darkest, 255 being white. And this is a nice little tool just to examine parts of your image. Just want to bring that to your attention. So we use the tool to do the contrast adjustment, but there's naturally also a function that can do it for you. And that function is called IMAdjust. And you just pass it the image, and it gives you the contrast adjusted image. And then you can compare your before and after using IMShowPair. So the way it works, you give it the original image, the second image you want to compare against, and the third argument, which is how you want to compare it. Do you want to blend them together, subtract them? In this case, we're giving it the montage operator, which will let you compare the images side by side. So now you do image adjustment, show pair, and I can see your dark image and the image contrast. And you can compare and contrast them. So you can also do a histogram of an image, just like you can do a histogram of any data. And in this case, this is a special histogram for images. So you can see the distribution of colors in your image. And this is often a good way to tell if the colors in your image are being smushed to one side and you're not making full use of the color spectrum. So if you did IMHist, which is the function that does histogram equalization on images, on this image, you'll find that most of the values in this image are dark, with very few, if no, light values given by this distribution. And you can see them here. The majority seem to be less than 100, with even more being in the low 0 to maybe 25 range. And taking this information, you can do what's called histogram equalization. So histogram equalization works, at least on a large scale without going too deep into the math. It tries to redistribute the colors so that rather than everything being smushed to one side, you make use of the full color spectrum and push the values of the lesser known, lesser used values to accommodate the full spectrum. So now you are leveraging the full color range rather than just a single part. And what this ends up doing to the image is now you can discern more parts of your image that you couldn't be able to tell with before. So for example, before you couldn't really tell there was anything on this desk over here, but now you can tell there's actually is a wall here. There looks like there's a circular device here and everything. And it works. All right. Next thing, sharpening images. First, I want to clear up some misconceptions. So there's a popular CSI meme of like enhancing images where they see some person on a CT image and then they zoom and enhance, zoom and enhance, zoom and enhance, and all of a sudden they can read like the license plate or some reflection off a person's glasses or whatever. That is mostly false. You can't really do that. You're restricted by whatever you see, whatever pixels you have at the moment. However, there have been recent advances in AI and machine learning algorithms that can do something like this. If you're interested, you can look up this GitHub page, which is for neural enhancing. And let me see here. And this is really interesting, where it can turn pixel images very clear using a neural network code that they design. And this is based in Python. But in case you're interested, I've linked this in the PowerPoint slide so you can take a look at it. So how are we going to do image sharpening in MATLAB? So we can use the IMSharpen command. So what this tries to do is it tries to find changes in the image. So where you're going from, let's say, a dark pixel to a lighter pixel, or vice versa, from a lighter pixel to a dark pixel, and it tries to enhance that difference. So essentially, it tries to make sure that edges are being kept and emphasized, and everything that's not an edge is not being emphasized. So you can read it in your image that you want to sharpen, do IMSharpen and call the image, and then show IMShowPair to compare and contrast them. So you can see here, you have the original rice image, and you can sort of see the values here. And if I try to zoom in on a single rice, you can sort of tell where the edges are, but not too much. If I zoom out, and now I take a look at its equivalent after it's been adjusted, you can better make out the edges here. All right. Next thing is noise removal. So this is probably the closest thing to movie magic I can show you. So here's how it works. If you take a look at this image, this is what we're going to be calling salt and pepper noise. So salt and pepper noise, you might remember if you ever turned your TV onto a channel that didn't have a signal. It just looks like white static noise. And there's actually a very specific way you can remove this noise using MATLAB. And the way you do it is using a median filter. So the reason why you can do that is this salt and pepper noise is always going to be either 0, black, or 255, white. So what you can do is, if you have a regular image here and it's being corrupted by salt and pepper noise, you know that the regular image has values from 0 to 255, but the salt and pepper noise is either only going to be 0 or only going to be 255. So chances are, if you take a look at any subset of the image, and you take a look at the pixel values, you'll see values that range from 0 to 255, but the values that correspond to the actual image are probably going to be more near the center, while the values that correspond to the salt and pepper are going to be the outliers 0 to 255 that probably aren't going to be found in your normal image. So what you can do is a median filter, whereby you take a look at a small little subset of this matrix, and for every value you're examining, you replace it by the median of the entire set. So this works beautifully because salt and pepper noise is always going to be either 0 or 255. So if you always replace every value with the median, the values that are 0 and 255 are automatically going to get removed. So the 0 here gets replaced with the median of the values around it, including the 0, and because 0 is going to be pushed off to one side, this gets replaced with the median, which is 204. So if you load up an image, which is going to be the rice image we had before, I'm going to use IMNoise to add salt and pepper noise to it. And in this case, I'm going to say replace 70% of this image. Yeah, we don't have a sign sheet, but thank you for coming. It's going to be on YouTube along with code. So I'm going to replace the image with 70% noise, and then we're going to see a compare and contrast between the original and the noise version. So you probably can't even tell that there's a bunch of rice in this image. It just looks like noise. But with a median filter, we're going to be able to remove the majority of this. So in this case, I'm going to do a 6x6 matrix, in which case I'm going to look at 6 rows and 6 columns and take the median of those as I'm scanning across the image. And that's what this median filter will do. If I run this, all of a sudden, all this noise got turned into this image. So the cell, naturally, it looks like you lost some details on the rice, but you still recovered the majority of the image, which you probably wouldn't have been able to even tell there was anything in this image before. And you can play around with this though. So let's say only maybe 50% of the image was corrupted. So in this case, you can sort of tell there's something there, but not quite. And now if you run this, you can better see the rice. You can start playing around with the filter. Maybe do a 3x3. See maybe if I reduce the noise even more. And in this case, it pretty much removed all of the noise as well. In this case, you pretty much recovered the entire image, even though it was 25% corrupted. So it's good to know. And the last thing I want to show you guys is how to do noise removal using a convolutional neural network. So in my work, I can't really extract information from an image if it's noisy, because the noise is part of the information I don't want. So oftentimes I don't really know what type of noise I'm dealing with. So it's never as straightforward as the salt and pepper noise, or there are other types of noise you can run into. For example, some noise in images have like patterns to them. So if you ever see an image that has a bunch of like scan lines on them, that's a type of noise. If you ever see a bunch of dithering dots on an image, that's a type of noise. And all those have methods you can remove them. But oftentimes when you're doing microscope images, you see this sort of weird graininess to the image. It's not any specific kind of noise, it's just noise that exists. And what you can do instead is remove them using convolutional neural network. And MATLAB has a built-in neural network called DNCNN. And the way it works is you just call the neural network, save it as a variable net. You have your particular image that has noise here that you want to remove. And then you just call the denoise image function, pass it your image and the neural network you loaded, and then it removes the noise in the image. And takes a couple seconds to load in the neural network. And I found that this neural network works really well for noise and images that you're very unsure of, as long as it's not too intense in the image, because it does have a tendency to smooth things out. So in this case, you can see here a lot of the graininess has gone away, and now you can see the smoother transitions and on the subsurface of the cell better. And now I can start using this image for analysis purposes later, without having to worry about the noise here. And that was it for image processing. And the last part we're going to do is signal processing. Any questions before I continue?
So if I understand correctly, the neural network convolution filter is going to remove waves or things that look wave-like.
I'm not entirely sure how this neural network was trained, so what kind of noise it does remove. It just has a tendency to remove noise that doesn't have any particular shape to it or pattern to it. So if it's not something like this or waviness or something that has a pattern, and it's just some sort of abstract noise that's just in your image, it can remove it at the cost of possibly smearing some stuff.
Yeah, thank you.
No problem. All right. If there are no further questions, on to signal processing. So oftentimes you don't just want to plot your data. You often want to glean additional information from your data, as the case of this example, where they apparently had a recording of the dry bulb temperature at this Logan airport across a number of days, apparently. And they're recording the temperature that was recorded. And you can see here the hourly temperature is very random almost, but it seems to follow some sort of trend. And if you average it over 24 hours, you can sort of better make out the behavior of the signal over time. So what we'll be going over in signal processing is some general tools, just like we did for image processing, how you can do Dtrending, how you can smooth out your signal, how to filter part of your signal, and then how to do peak finding. And the example we're going to do is an ECG signal. So naturally, biomedical engineer, electrocardiograph signal, something normal that we'll probably run into sooner or later. And this is an electrical recording of the activity of the heart. And depending on the shape of the signal, the spacing between the peaks, a physician can discern the state of your heart and if it's behaving properly without having to actually look or hear it. And often in the doctor's office or in the hospital, they have an ECG monitor hooked up that is tracking this based off of electrodes that they apply to your skin. And in this case, we're going to see if we can start analyzing and try to see what information we can glean from this corrupt ECG signal I made for us. So our goal is going to be to recover as much of the actual signal as possible from this, and then try to glean some information a physician can use. So I have this signal as an Excel file, and you can use a read matrix command we did before, and then we can plot this signal up. So let's go ahead over to MATLAB. I have it right here. So if I open this up, we have one column as milliseconds, one column as millivolts voltage, and it's just very straightforward signal. So if we go ahead and plot it, you can see here we have something that looks like an ECG signal. There seems to be this other sort of contaminating signal that is interfering with it. So how do we start fixing this signal? The first thing we need to fix is, usually when you see these ECG signals, it's nice and flat and repetitive. So our signal seems to have a sort of sinusoidal wave to it or something. So we need to what's called detrend our signal. So to detrend it means we need to center it around 0. And you can first try doing what's called a linear detrend, which is the most straightforward. So it assumes that there's some sort of linear corruption in your data, and it just subtracts that after doing a linear fit to your data. And in this case, it's not going to make that much of a difference because clearly we can see this is not a linear trend in our data. It seems to be a nonlinear trend, actually. So when you try to do this detrending using this code here, it's not going to fix your data that much. So if I go back here, and I run this part of the code, it's not really going to fix the signal much. Maybe it perhaps helped a little bit, but not as much as we want it to be basically a flat line at 0. So instead what you can do is called a nonlinear detrend. So one of the parameters you can give to the detrend is a polynomial fit. If you don't give it a value, it just automatically assumes a linear trend. If you give it a value, it tries to do a polynomial fit of the order that you give the second input. So in this case, I'm going to decide 5th order, let's say. And you can say voltage, 5, detrend. And in this case, you can see we have a nicely detrended detrended signal based off a 5th order polynomial fit. So now you can see it's centered around 0, as we intended. So next thing we want to get rid of is this sort of part of the signal. So clearly, this large spike here at R corresponds to these spikes here, but then we can't really make out the P, the Q, the S, the T from this signal. So it's hidden inside this very fast moving part of the signal right here. So we can remove them using a filter. So before I explain how, we need to first talk about what makes up a signal. So if you take a look at this signal right here, it looks noisy, messy, chaotic. However, if you take a closer look, you'll see it has patterns to it. You'll notice that the signal seems to oscillate slowly like this, but then there seems to be a sort of faster oscillation like this, and then an even faster oscillation that's hidden inside the signal. So it's sort of like it's made up of 3 different signals. And in fact, it is made up of 3 signals. So the signal, the back signal is made up a little bit of the red, which is a bit slow, a little bit of the green, which is a little faster, and a little bit of the blue, which is accounting for the very fast part of the moving signal. And what you can do is if you have your signal, you can add these 3 together and you can get your final signal out. And you can go backwards as well. So if you have this signal, you can go backwards and reconstruct the parts of the signal that it was made up of. And this relationship between them is called the frequency domain characteristics. So if you have your original signal here, you can decompose it into a bunch of sinusoidal frequencies. And this entire process is called Fourier transformation. So you have your signal here, and if you deconstruct it into its sines that make it up, they each have a specific frequency they oscillate at. So this is a low frequency here, even higher here. And if you have this, you can actually remove noise in your signal. And the way it works is we essentially tell MATLAB, all right, break down this signal I have here using the Fourier transformation, and I want to remove every type of signal that is, let's say, between this and this many hertz. And it will try to remove that from your signal and then give you whatever's left over. And in this case, we have this signal right here, and this fast-moving part of the signal right here seems to be a very high oscillating signal. So it's a high frequency. So we can use the design filter command in MATLAB to design a filter to remove this. Now, I know based on prior experience that this fast-moving part of the signal is what's called line interference or 60 hertz line interference. So in the United States, we have 120 hertz. So we have the 60 hertz AC frequency that usually tries to infiltrate your signals through just power outlets. And usually in common filters for devices, they remove these using capacitors. But if you don't have that, it's going to interfere with your signal, and you're going to see this 60 hertz noise in your signal. So what I'm telling MATLAB is, okay, cut off everything from 59 hertz to 61 hertz, and give me whatever's left over. And because I know this is 60 hertz line noise, if I remove everything from 59 to 61, I'll remove the 60 hertz noise, and MATLAB will just give me whatever's left over. And in this case, after you do that, all of a sudden you can better see your PQRS points here of your image. So you can now better see the image here. You can better make out the PQRS T parts of your intervals. Next thing we want to do is it's a little bit noisy here, and even though you can tell the PQRST are probably located around here, 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 it'd be better if you just start smoothing the data. And this extra noise in your image usually just comes from anything non-specific. So it could be a motion artifact, so the person was moving when they recorded the signal, maybe some noise in the room was doing it. Even I've seen this happen before, having the lights on in a room can affect your signal. So maybe that was causing some sort of issue. So now what we can do is the smooth data command, which uses a moving average. So it tries to smooth out the values as it's moving along the graph. And when you smooth out this signal, you get these values right here. And now you can better say, okay, it looks like the peak is here for our Q, for P, Q, R, S, T, and then you can better make out the values here as you're going all along the way through them. And if you don't like coding too much, this is a perfect spot where I can introduce to you the signal processing tool. Just like there was an image processing tool and tools for other programs in MATLAB, there's one just dedicated for signal processing. And the way it works is you just type signal analyzer or signal analyzer in the signal. So you can type in signal analyzer and your signal. So we have original signal. And this will open up your signal here. Give it a couple seconds. So now you have your signal analyzer app. And it tries to plot your signal. And it seems to want to plot everything. It doesn't really know how to plot it. So in our case, the first values are the time, which we don't need. So I'm going to delete that. The second part here is actually our voltage, which is what we actually want. So perhaps it might be better. Click voltage here. Yeah, so we have our voltage here. You can assign time info. Actually, I know what the sample rate is for this. So sampling rate was 1000 hertz, starts at 0, and now we have better delineation. So you can see time here on X, and our voltage in millivolts on Y. And now what you can do is, for example, if you go here to Analyzer, you can smooth, filter, bandpass, whatever. So let's say we do our little band stop. I want to get rid of 59 to 61 hertz. Run this. And it automatically ran our smoothing filter to it. Then you can do a smooth onto it, moving mean. And now you smooth out your signal here, and you can export this afterwards, and or generate a function however you want to deal with it. So if you don't want to code, you can just work on just this. And bye, Izzy. This will be on YouTube, so don't worry about it. Go off and get to class. So I'm just going to not save this. Now, the last thing is, now that we have our signal, we can actually start analyzing the peaks and try to figure out the characteristics of the signal. So we can use the find peaks function to figure out the peaks of our signal, so the local maximums and minimums of our signal, by just passing in our signal and trying to see if we can give it a little threshold information. And one nice thing you can do is if you flip the signal upside down, all of a sudden this bottom part here is on top, and then you can use find peaks again to find the S. So you do find peaks once to find your R's, flip the signal upside down, and do find peaks again, and then that'll find your S. And then if you restrict your navigation range to maybe between here and here, and then flip your signal, you can find your Q values here. So using these tricks, you can all of a sudden create and figure out where the PQRS parts of your signal are. And using this information, you can figure out your QRS interval, which is one of the parameters that physicians look at to judge how healthy a person's heart is. And in this case, if we figure out the QRS interval based off these values here that we recorded for QRS, we can take the mean of the values we get, and I got 55.5 milliseconds. And I know based off prior experience that the normal QRS is generally under 20 milliseconds. So the fact that this is a bit faster indicates that this signal comes from a patient with a presence of arrhythmia. So this is something that a physician can use. Naturally, the devices that they have will probably already notify them of this. But if you're just working with the data on your own, this is how you would arrive at this solution or arrive at this conclusion. And questions?
Yeah, I was impressed with, what's it called? The one where you filter the filter tool for the signal processing. That was pretty cool.
Yeah. It always is nice to have a lot of these MATLAB things that you have to program. There are a bunch of just apps that do it for you.
Yeah, I didn't know we had that. So good to know.
All right. Claudia, any questions?
No, I think everything's fine. I just have to go over some stuff, but for the video, it's fine.
All right, works for me.
Thank you.
All right, well, thank you guys for coming. And for the rest of you guys, I'll see you on YouTube. So I hope you guys can catch up with your MATLAB and stay up to date with your skills. Take care, everyone.
Thank you, you too.